Lesson 15. Electromagnetic wave. Section 15.2. Maxwell's equations. We have learned about these laws and properties of electromagnetic field. The equations grouped here are called Maxwell's equations. Those are, from top to bottom, Gauss's law for magnetism, Ampere's law with Maxwell's correction, and Faraday's law. Faraday's law includes only the term for time-varying B. The term for time-varying S, as in the case of a moving conductor, is not considered. Maxwell's equations describe how electric and magnetic fields interact and propagate. Let's see how electromagnetic wave propagates in free space, where neither charges nor conduction currents exist. This is the set of Maxwell's equations for free space. Section 15.3. Electromagnetic wave. Let's focus our attention on these equations. In free space, the relative permittivity epsilon r equals 1, and the relative permeability mu r equals 1. Let's take Cartesian coordinates x, y, z, with the x-axis oriented upward. Assume that E and H are given by these equations and are uniform in the xy plane. E and H change with respect to z and t. Z is the coordinate on the z-axis, and t is time. C is a constant. Let's examine how E and H satisfy Ampere's law and Faraday's law. By substituting E into the right-hand side of Ampere's law, we obtain this equation. The left-hand side of Ampere's law is derived to be this equation. To satisfy Ampere's law, these two equations must be equal. Therefore, the terms highlighted in red must be equal. The next step is to substitute E and H into the equation for Faraday's law. Starting from the right-hand side, we obtain this equation. Evaluating the left-hand side, we obtain this equation. If these terms are equal, Faraday's law is satisfied. These are the conditions under which E and H simultaneously satisfy both Ampere's law and Faraday's law. By eliminating Hm and Em from the above equations, the relationship between C, epsilon 0, and mu 0 can be derived. The value of C is given by this equation, with unit of meter per second. Epsilon 0 and mu 0 are the constants in vacuum. This is the speed of light in vacuum. The relationship between the amplitudes Em and Hm is given by this equation. This E and H pair has been shown to satisfy both Ampere's law and Faraday's law. By setting z equals 0, we can see how E and H at z equals 0 change with time t, as shown in this slide. Next, with time t fixed, E and H vary along the z-axis as shown in this figure. As time progresses, the waveforms propagate in the direction of z. By keeping the phase at 0, we can see how the front edge of E and H propagate. As we have seen, E and H propagate as waves. The speed of propagation in the z direction is given by this equation, and it is equal to the speed of light in vacuum. The plane in which E and H are in the same phase is called a wave front. The electromagnetic wave expressed by these equations is called a plane wave. The wave front of this plane wave lies parallel to the xy plane. Exercise 15.3. This is your homework. This is another set of E and H that satisfy both Ampere's law and Faraday's law simultaneously. Find the direction of propagation of the electromagnetic wave. Pause the video and answer the problem. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.